All right, time for the easiest lecture of the chapter. Just section 3, Thermochemical Equations. All right, clicking away here. All right, so thermochemical equation, what is it? It's just a balanced chemical equation where they add in a little blurb about the energy change. So this right here, ammonium nitrate. So NH4NO3, it's ammonium nitrate. And when you dissolve it in water, you get ammonium ions, you get nitrate ions. That's a balanced chemical equation. Ta-da! Now it's a thermochemical equation. All right, so now I put in a delta H. All right, and by the way, delta H is positive. So when you have a positive value of delta H, what does that tell you? It tells you if this process is endothermic or exothermic. And so what is it? You have half a second. All right, it's endothermic. All right, so that means it's energetically uphill. If you were to actually like hold a beaker in your hand and dissolve some ammonium nitrate in it and stir it around, it would feel cold. You'd feel it get cold because it's going to start pulling energy from your hand because it's an endothermic process. All right, there's something called the enthalpy of combustion or the heat of combustion. You might see a delta H with a little subscript COMB. Looks like delta H comb. All right, this is the heat of combustion. It's the enthalpy change for the complete combustion of 1 mole of substance. Now, because the heat of combustion is by definition the enthalpy change for the combustion of 1 single mole of a substance, you're going to commonly see fractional coefficients in the equations. All right, so like a lot of our combustion equations that you've seen, like C4H10. Yeah, go off and try to balance that one right now. All right. But what you're going to do is you're going to skip the step where you double everything because, the oxygen is going to come out to some weird number. You're going to leave the oxygen as, whatever it was, 13 halves or something screwy. All right, that's totally fine because for these combustion reactions, they are, by definition, for the combustion of 1 mole of stuff. All right, so you will have to have fractional coefficients on some things. Yes, this. Oh my gosh. Standard conditions. There's a long story, not a long story, but like all the way into college, I was a chemistry major, and all the way into college, I kept tripping up on standard conditions. I would confuse it with STP. Gee, I wonder why, because, standard conditions, standard temperature, pressure. Standard conditions are 1 atmosphere and 25 degrees Celsius. STP, 1 atmosphere, 0 degrees Celsius. They're really easy to confuse, and I was confusing these all the way up into college. Whenever I needed to use 0, I used 25. Whenever I needed to use 25, I used 0. I was always messing them up. Really annoying. But you're going to see this little superscripted naught, this little like degree sign that's up here. All right, that just means that it was determined under standard conditions. So there's a whole list of standard conditions. All concentrations are exactly 1 molar. All gas pressures are 1 atmosphere. The temperature is 25 Celsius. Solids are pure solids and all that stuff. All right, so that's that. Let's get to this next one. All right, so when you're dealing with thermochemical equations, you need to definitely pay attention to states. So what do you think has more enthalpy, liquid water or water vapor? So water liquid or water vapor? What do you have to do to liquid water to turn it into a vapor? You add heat to it, right? You heat it up, and enthalpy is essentially heat. So pay attention to the states, all right? There's something called the Molar enthalpy of vaporization, delta HVAP. We actually have seen this. We saw this, gosh, I forgot what chapter it was, but several lectures back. All right, it's the energy required or the heat required to vaporize 1 mole of a liquid at its boiling point to convert it into a gas. All right, and then we also had, let me click down here while I'm thinking of it, the molar enthalpy of fusion, right? That's the amount of energy it takes to melt 1 mole of a solid. So you have a solid, it's at its freezing point. So imagine you have water, ice, but it's solid, it's at 0 degrees Celsius. You'd have to put energy in to break that solid up and turn it into a liquid, still at 0 degrees Celsius. But the amount of energy you put in to convert the solid to a liquid is what we call the heat of fusion. All right, so going back up to this thing. So we have H2O liquid going to H2O gas. So liquid going to gas, so it's vaporizing HVAP. So that's 40.7 kilojoules for this process. For giggles, what about the reverse process? All right, so when I flip a reaction around, right, if I'm going from H2O gas to H2O liquid, what happens to this delta H value? The only thing that changes is the sign. All right, it's negative 40.7. So when I have gas going to liquid, like it has to cool off, right? It's cooling off. That's an exothermic process. So the gas has to release energy and it becomes a liquid. How much energy does it release? 40.7 kilojoules, all right? So it's negative. So that means exothermic. All right, that's actually this whole entire little section. Sweet. Now, buckle up. It's going to get some crazy stuff. You're going to see some gnarly equations in the next lecture.